a brightening in X-rays as a flare, but we categorize the flare according to how high this peak is. 10 to the minus 4, anything above that is what's called an X flare. 10 to the minus 5, anything above that is called an M flare. There are C flares. However, you can see in 2002, around solar max, the overall brightness of the sun is so high that the base is above C. So there could be C flares that are up here. These little peaks here are C flares. Okay, so basically I'm going to talk about flares, and I'm going to focus on the fact that this is how you can tell when it's a flare. It has to show up in X-rays. But that's really just to show you that it's a flare. This is the same event, but seen in 195 angstroms. Trace, which was a spacecraft that's no longer operational, was observing. And we're going to see what this flare looked like. Now, I'll draw your attention to a few things. Up here, we see plasma that, while you are not seeing the current sheet, you're seeing plasma that is related to something we will talk a lot about, a current sheet, a place where the magnetic field is reversing. Below that, you see all these wonderful loops forming underneath the current sheet. And they start forming a little bit later, or I should say they show up in this wavelength. This is about 1.5 million Kelvin. So you're seeing the material at 1.5 million Kelvin a bit later. And finally, I'll draw your attention even further down. Down here, you see this. This is going to be a very important part of our talk, where you see the places where the magnetic field is anchored, and that shows up. That's actually one of the most important parts of a solar flare, is that low atmospheric response. Okay, so here's how it all goes together. This is the GOES curve. This is the 1 to 8 angstroms. This is 0.5 to 4 angstroms, basically twice the energies in the photons. All these things just sort of peak together. Okay, now I'm going to take a little diversion here, because discussing flares, like discussing a lot of things in heliophysics, we get into a lot of jargon, as you've no doubt noticed. Does anyone know what epistemology is? Not a physics term. It's a philosophy term. Yes, that's right. It is the theory, the philosophical theory of knowledge, how we get knowledge. Practiced by people like Immanuel Kant, Karl Popper, one of my personal heroes, David Hume. And many of these people think knowledge, like we're talking knowledge of, how do you know that fire is hot? Basic things like that. How do you know the sun will rise tomorrow? Knowledge in these philosophical terms is thought to come only through sensation. What you see, what you hear, what you smell, what you feel. We haven't really gotten a lot of astronomical data through smell, but essentially all the data we have, everything we know about the sun, everything we know about everything has come through observation. And observations are always, when you come to flares, of a particular flare, right? You can't really make an observation of general flares. So what you end up seeing is data of very particular flares, like the old Earth Day flare I just showed you. And the data comes in the form of light curves, of spectra, of images, of image sequences like we just saw. Now, that's not science at all, I would argue. Much respect for the people who take data, it's just taking data, right? You have to sort of organize the data, and that's where we get a lot of our jargon and terminology. You basically take these observations and you generalize them, you categorize them, you make up terms for them. Eruptive flare versus compact flare, impulsive phase versus gradual phase, right? Does everyone agree? You start to hear these things and you're like, what does that mean? I've never heard that term before. Or even if you've heard it, you're like, I think I'm using the term eruptive flare differently than my colleague is. Okay, so there's a lot of effort that goes into this category here, but it's still not how we understand things, right? We have to take these categories and these things that we've arranged and understand the physics behind them, okay? And so now there's real physics, basically, and I'm going to talk to you about the real physics. The problem with this understanding, and when I say models here, there are people in our field who think models are just big numerical simulation. I'm just talking about, no, like a picture in your head that you can draw a diagram of that involves physics. That's what I mean by a model. And these are always being developed. Right? We don't have a definitive model for things. Otherwise, you wouldn't be here. Right? We would not be, scientists would not be engaged in studying solar flares because we would understand them. We do not understand them, so these models are being developed. I say this because in many places, including in the textbook, in the nice chapter written by Hugh Hudson, they tend to present things in the order that science develops them, namely observations and then categorization, and then they try to motivate models. Is everyone familiar with this way of seeing things done? Because this is the way it really is done. However, in my opinion, it's a crappy way to learn something new. It's much easier pedagogically to start with a framework, to start with how you understand something, work your way to, oh, according to this framework, that's why there's an impulse, if there's chromospheric evaporation, that's why there's an impulsive and a gradual phase. Okay, so I'm just going to motivate the fact that I am going to do something a little different than a lot of people who would give you a lecture on solar flares. I'm going to start with the basic physics and work my way backwards. And that is not, I am a theorist, so I sort of like to live in this realm, but I have the utmost respect for this realm, but I just think for trying to explain something to you, especially if you don't work in flares, this is the easiest way to go. Okay? So I will show you a movie of a model. It's a model due to Judy Carpin and Rick DeVore. And this looks a lot like models that Neil was showing yesterday. There's basically a bit of a sun here. There's some magnetic field lines being traced out. The color is actually the density, the current density. Okay, and these magnetic field lines here are going to be sheared. Oops, I think. And you'll see the current density is building up under there. You see this big eruption. You see all this stuff happening. This is both a CME and a flare. In the interest of clarity, I am not going to tell you about all the exceptions, flares that happen without CMEs, CMEs that can happen without flares. I'm going to focus on a very particular kind of flare, which is very typical and very typical of the largest flares. And those are called eruptive flares or two-ribbon flares, and that's the model you just saw was of that. You saw a coronal mass ejection. Neil showed you many movies that look just like that. Underneath it is a current sheet left behind by the erupting flex rope. Underneath that is the flare. And some people debate about this, but given the definition I just told you, how do you know the flare has to be down there? What is our working definition of a flare? X-rays. It has to enhance X-rays. Where are the X-rays going to come from? Dense material. Where is the dense material? It's down there. Okay? So if for no other reason, this is an artificial division, but that's how we've made the division, and that's where the flare is. It has to be connected to the solar surface because it has to get the material needed to generate X-rays. Okay, so we're going to focus just down here. What happens to the flare? And the 4 parts of the model, not a numerical, that was a numerical simulation. I'm just going to talk about a simple model. It's often known as the CSHKP model, the Carmichael, Hirayama, Sturrock, Kopp, and P stands for Newman. Figure that one out. Model of an eruptive flare. We have 4 phases, basically. We have the release of the magnetic energy. I'll talk to you about that. That's where the energy comes from to produce all the other effects. We have the downward transport of energy from where it's released in the corona. It either goes down by thermal conduction, that's a kind of fluid picture, or it goes down by non-thermal particles. Beyond that is the evaporation. Loops are filling up with hot plasma. This is basically, although people will talk to you about flares emphasizing this, This is the only part that really defines it as a flare according to the way I said. If it doesn't have chromospheric evaporation, it ain't a flare because it isn't going to produce X-rays and you're not going to be able to call it a flare. Okay, so this is actually, people will gloss over it. This is the most important part when it comes to talking about flares. And the loops, after they fill up with hot plasma, they cool down. This is 95% of all the observations of flares are of these two things. There are observations of the energy transport. Very important because they help us understand that. Very difficult. Release of magnetic energy, I would argue there's no observations of that. It must happen, but we can't really observe it. So it's all, that stays in the realm of modeling. But the downward energy transport, we have radio, we have X-rays, we can see stuff like that. And here's how they all fit together into this classic picture. Now I have only half the loop. There's another half over there. These are those loops. This is that current sheet I pointed to. So we have the release of magnetic energy. We have the downward transport of that energy down into the chromosphere. We have the evaporation, the most important part of the flare. And we have the loops filling and cooling, and that's the last part, in my opinion, the most beautiful part of the movie I showed you. So far, so good? Yeah? Oh, you missed an awesome movie. Those relate to that movie. That is, as those loops fill, that is where they get up to. Okay. But ignore that because we're going to sort of go into cartoon land. This was an image that was supposed to motivate this kind of picture. This to show you, yeah, this is not totally outrageous. This is a simplification of what we really saw. I'm going to go even more cartoony, although this has got real math behind it, if not physics. It is a model based on Terry Forbes and Jun Lin. They worked out the mathematical formulation for this in terms of conformal mappings. Beautiful stuff. What you're seeing here are magnetic field lines in blue that go up and over. There's a flex rope. This is the CME. I want to talk about energy release in a solar flare, not the CME. So I'm going to do something completely artificial. I'm going to fix this rope in place. So when I talk about energy, you can't say, well, a lot of that energy went into the CME. In reality, that is true. In this cartoon, that is not true because I have imposed my will on the mathematics and forced that to stay in place. Below the flex rope was that current sheet. Here we have the current sheet. It is an exact discontinuity in the magnetic field in this simple model. There is a density of current. That is, the magnetic field is going up here and down here. So you can work out what the surface current K is. And I plot that surface current as a function of height here, right? So it's 0 here and here because there's no current over there. I don't plot that current. This is the current in that current sheet. So this is K, the number of amps per meter in that surface current. If I integrate that, I get the total current in amps being carried by this current sheet. It's going to be very important. Down below here, I have the field lines that will be, oh, you can't really see. Oh, that's too bad. This is sort of grayish, and that's sort of grayish as well. I'm not even going to play with the lights. Just trust me. These are the field lines that have been reconnected. Because how is this energy release going to happen? It happens through reconnection. And then in the little yellow boxes, this is the range of the chromosphere, of the lower boundary where those reconnected field lines are anchored. Right? So I'm just drawing right there what those are. Those are known as the ribbons. Here's a movie of this thing happening. What you're seeing, you're not seeing the gray, I'm sorry about that, but you're seeing field lines being brought into that current sheet, reconnected, and formed into these underlying arcades. This is where the flare will be. This is where we're going to focus our attention. So is everyone comfortable with this model? What's happening to the current in the current sheet as the flare, as reconnection occurs? The total current, number of amperes. What's happening to that? Can you integrate with your eye? The area under that, as time moves forward, the area goes down. Yeah. This is what reconnection is all about. Decreasing the current in the current sheet. Okay? That's all it really needs to do. It's decreasing and it's also increasing the amount of flux in this, right? The number of closed field lines, you see them, they start at 1 and they increase up to 5. So we've got 4 new field lines that I've drawn. There's a certain amount of flux in Weber's or Maxwell's underneath that. If I plotted both of those curves, here's the total amount of current over time. It starts out at, well, this is all non-dimensional, but it starts out at some level and drops to 0. That's what we saw in that cartoon. The total amount of flux underneath starts at some level and increases. This is basically the story of magnetic reconnection. If you take the current and the flux, and instead of plotting it versus a function of time, I plot one versus the other. I plot current versus flux. Now I'm in a position to do this integral. The integral I d phi is, if you go all the way back to probably sophomore year of college as a physics major, this is the electromagnetic work done by the reconnection. The amazing thing is, you heard on Wednesday, or on Thursday actually, I guess, or no, on Wednesday, how complicated the process of reconnection is. But one thing that's very easy is you can work out how much energy it is liberating. And this is it. So the total amount of magnetic energy in this is higher than this, and the difference comes from that portion of the integral. So if I work out that integral, I know how much energy has been released by the solar flare. Just the area under that curve. So far, so good. It's very simplistic. I will also say, if you were interested in the reconnection electric field, you could take the slope of that. From what I've just said, as interesting as that number is, it's not relevant for this story. It might tell you how the magnetic energy is converted, but I just want to know how much is converted. Okay, now we'll go to reality. This is an image of the solar chromosphere. This is being made at 1600 angstroms. It mostly shows 100,000 degree plasma. And here at the same time is 1 million degree plasma. And this is a different flare. And you can see the two parts to it. The cool foot points, this is what I was showing in orange, are spreading out from each other. Does everyone see that? They're separating. That's really exactly what was shown in that cartoon. In fact, one of the reasons I've shown this flare, we name these all after holidays, so I've come to call this the, there are people here from the UK. Neil isn't here. Anyone recognize that day? It's Boxing Day. This is the Boxing Day flare. Yes, this is Boxing Day, the day after Christmas. Yes, the Boxing Day flare is very, very two-dimensional. Does everyone agree? I mean, these ribbons are straight lines. So if there's any flare that's going to look like this cartoon, it's the Boxing Day flare. And those ribbons, right, tell me how much flux has been reconnected. So here is the image in 1600. And if I take every pixel that is brightened at the instant it is brightened and color-coded on a map of the magnetic field, that's what I have here. So the earliest time, about 15 minutes past the hour, past 11 o'clock, 11:15, we've colored in black somewhere in here, and then in purple, blue, etc. You see on the map the ribbons are moving outward. And as they do so, they're covering up more and more magnetic flux. This is the magnetic flux being reconnected. We're seeing it on the photosphere or the chromosphere in these ribbons because, as I said, that's the easiest place to observe. However, we can make the calculation, and let me also point out, it is very, very hard to see magenta color. I can also, this is two-dimensional roughly, but it is 75 megameters long. So I'll just use that number a little bit later. If I tally up all the magnetic flux that has been reconnected, I get something, and the error bars are now basically the thickness of this line. This is the amount of reconnected flux as a function of time, okay? And it goes up to about 1.5 times 10 to the 21 Maxwells. That's how much flux I reconnect. Remember, if I want to know the energy in the Boxing Day flare, I only have to do that integral of I d phi. Here I have delta phi. The integral of I d phi is basically going to be 1/2 whatever the initial I was times delta phi. How much current? Well, I can't observe current, so it's hard to measure it. I can use some freshman physics, though, sophomore physics. Right? Current and flux are related through, you guys were sophomores once, right? The ratio of flux to current. When you did circuits in sophomore year, flux to current. I know I brought this up on Tuesday, too. Came up for a different reason. We were looking at a little circuit. Inductance, yes, it's self-inductance. And your self-inductance is? You as a human being have a self-inductance. Everyone has a self-inductance. Anyone remembers their self-inductance? What? On the order of microhenries, exactly. Self-inductance is just length. So assuming you're like 1 meter, 2 meters, 3 meters, right? As humans, you don't even really have to be, as astronomers, you don't have to be that precise. Right? So if I just put in the length, I've got the energy. The energy of the Boxing Day flare, 1.2 times 10 to the 31 ergs. Right? The minute you can measure that and you can measure the actual size of the flare, you've got the energy that was liberated. This is number 1 on our list. You can also measure the electric field. As I said, not so important. We know that we have this much energy. It's come out of the magnetic field. It was converted, or electromagnetic work was done on the plasma to this tune. Total energy, yes. 75 megameters. From the beginning to the end of this. It's really, right, it's based on a 2-dimensional cartoon, so you get energy per unit length. And I'm saying, well, it's 2-dimensional for a long ways, but not forever. So I put in that, so we have a total amount. So that's where that. Okay, so far so good. We're a quarter of the way done. Now we have to get to the tricky part of transporting that energy. Electromagnetic work was done up here by this reconnection, and it has to make it all the way down to the chromosphere, because if it doesn't, we don't have a flare. Right? Some energy will not do this. And so this is the energy that the magnetic field releases. This is not the energy that goes into the flare. The energy that goes into the flare is however much makes it down into the chromosphere. Now, the way, regardless of which of these mechanisms we focus on, essentially the only thing that's going to carry that energy down is electrons. Because they are the more mobile particles we have in our plasma, and so they are going to carry the energy. Now, if we think about electrons, we're going to go back to something else we talked about on Wednesday, which is collisions and cross-sections. As the electrons make it down from the top, they will collide with particles from the plasma. Right? The loops are not empty. They're actually quite full. And the electrons that know about this high energy are moving downward, but they're colliding. And the Coulomb collision or Rutherford scattering cross-section for scattering, if you go back to, again, this is kind of junior level physics or senior level physics, is a cross-section in centimeters squared, and then it scales with the energy of the electron. And here I'm expressing energy in kilovolts. So 1 kilovolt electron has a scattering cross-section of 10 to the minus 17 centimeters squared. This is just the Rutherford scattering cross-section. So when the electron's on its way, it's going to run into things and stop. Now, I'm going to quiz you again on something I told you on Wednesday. If you integrate the density of electrons that you're going to scatter off of times the scattering cross-section and integrate that along the path, when we were talking about photons, I called that the optical depth. Here, it doesn't really get a name all by itself, but when it's equal to 1, I've gone 1 mean free path, and there I have, on average, I will have scattered once. Does anyone remember the chance that I will not have scattered? The probability. 1 over E. Well done. You remember. Yes. So when I say it stopped, I really mean with a probability of 1 over E, that electron will have been deflected or given up its energy. Okay. nevertheless, we're going to use that and define something called the stopping column. If I integrate all the stuff down to along some distance, when that is equal to 1 over E, we call that the stopping column. If you ever do real, like, nuclear safety physics, you're going to learn this. If you want to shield yourself from X-ray, gamma rays, alpha rays, beta rays, you want to be behind a certain number of electrons. You want a certain number column of electrons between you, and it has to do with the energy in those electrons. And that stopping column scales with the electron energy squared. Okay. So let's take a 3 kilovolt electron produced up here. This is an example. And it would come if the material up here were 30 megakelvins, the average energy in our photons would be, in our electrons would be 3 kilovolts. So I've just chosen this 3 kilovolt number because that's what we might expect up there. What is the stopping column? You plug that in here. It's just basically 10 to the 17, the number of kilovolts squared. 3 squared is 10 in my book. So 10 to the 18. How far down will that electron make it before it, quote unquote, stops? Well, if the density in the corona is 10 to the 10, in these loops is 10 to the 10, it makes it 10 to the 8 centimeters. This is really simple math. That is a megameter. That is not far. Okay, so it travels that far and then stops. Or gets what it really does. It doesn't really stop. What it really does is it finds other particles that it scatters with and it exchanges energy. Now, if all those particles are much colder than 30 megakelvin, then it's a one-way exchange, right? It's like when your parents give you money when you're little. They have a lot of money, you don't have much money. The exchange goes in one direction, right? However, with your friends, if there's an exchange, hopefully your friends have the same, roughly the same amount of money you do, and the exchange goes both ways at times. So one hopes. So eventually the electron will lose its energy and basically just keep exchanging, or it's among a lot of 30 kilovolt electrons, and within this top 1 megameter, they're just exchanging with each other. And the ultimate outcome of such an exchange for particles is a Maxwellian distribution. The probability of various energies goes as e to the minus energy over kT. This kT is the 3 kilovolts, but there's actually a distribution of energies around 3 kilovolts. Maxwellian, thermalize. When you have 3 kilovolt electrons and you, within 1 megameter ball or maybe a 5 megameter ball, the electrons will all exchange energy and you'll have a ball of 30 megakelvin electrons. So far, so good. Let's consider 50 kilovolt electrons. It's not a huge difference, a little over a factor of 10. But we square the energy, we get a stopping column of 3 times 10 to the 20 centimeters. Play the same game, say, oh, how far does that go in 10 to the 10 centimeter stuff? That's actually like half of the solar radius. It does not go that far. It basically goes all the way through this and doesn't stop. Okay? So you have to get to the lower part of the atmosphere, the chromosphere, where it jumps up from 10 to the 10 to 10 to the 12 and then keeps going, and you will go into that. You can calculate how far in you go. It is the density scale height, basically in the log plot, that slope, times the log of the stopping column over, blah, blah, blah. It goes a megameter deep. Okay? The big difference here, we had a 3 kilovolt electron, and it just, stayed up in the corona trading its energy back and forth with other really hot electrons. The 50 kilovolt electron, it goes all the way down the loop and gets about a megameter into this high density chromosphere, deposits its energy there. Okay? This will not have scattered. It will not have exchanged energy with anything that has a similar amount of energy. So, Maxwellian distribution, that was really big when we took statistical mechanics, right? Everything has Maxwellian distributions. So these electrons going to have a Maxwellian distribution? No. This is what Dr. Merav Ofer was telling you about. The distribution function here, you have to solve a lot of complicated equations. Suffice it to say, the answer to those will not be a Maxwellian. And often what we see is a non-thermal, a power law tail. Okay? So in flares, when we see the electrons that are carrying the energy, we see two parts. We see the lower energy electrons, which are scattering a lot and forming a Maxwellian distribution. That we call the thermal part. And then they're the ones that do not scatter and therefore have the distribution function that satisfies some horrific equation that we will not talk about that equation on a Saturday morning, I promise you. So that's it. And when we make observations, these are observations by the RESI spacecraft in hard X-rays. Well, you see the loops we were talking about. This is actually 193, very similar to the wavelengths I've been showing you. These contours are the emission from hard X-ray photons, 6 to 8 kilovolt photons. But, right, I've been talking about electrons. Really, these are coming from electrons that are about that energy or slightly higher. Those are the green contours right there. Remember, these are the ones that don't go very far. So they get stuck at the top, trading energy back and forth. That's the thermal source. When we look at the spectrum, this red curve is the photon spectrum from a thermal distribution of electrons. In this case, they're only 17 megakelvin. Right? I was telling you they were 30 megakelvin. This varies for every flare. We see a different temperature, but there's this thermal source. But there's also this emission here. These are the electrons that did not scatter. They're stopping in the chromosphere. They have this power law distribution. The photon energy, anyway, goes as energy to the power minus 3.4. And there you see it. That, again, varies with every. Unlike the story the nice, I think very elegant story you heard from Merav Ofer, where shocks will always create the same power law, flares don't do that. The power law in the flare varies by the second, and we measure it by the second, and we see it change. At this instant, it was 3.4. But those are the electrons that have gone all the way down, and they don't stop till they get there. So this is a very typical picture of a flare. You have the loop top source. You have foot point sources. The foot point sources are the high energy electrons that didn't get stopped. The loop top source are the low energy, just merely kilovolts, that get sort of juggled around. Very interesting topic. This is probably related to the reconnection process itself. There are other electrons up here that are trapped somehow because we know they will not scatter. Right? They can go the distance, the whole radius of the sun, they wouldn't scatter. They're somehow confined to a little blob. I'm not going to talk about that. That's very, very interesting physics that's basically being done as we speak. All right, but if I want to take us away from this complicated equations. As I said, it's Saturday morning. I don't want to be solving equations like this. And get on to what would happen in cases, and there are many such cases. Yeah, question. Yeah. Yes, these are all confined by collisions. This loop top source. This is collisional. Yeah. I will also say there are discussions of if collisions are also augmented by a magnetic field geometry. In my own personal opinion, which is mine, I'm trying to get my colleagues to believe me, there are shocks involved with confining this material. They don't confine the electrons per se, they confine the plasma, and the electrons are part of the plasma. But yeah, because there's a big pressure gradient here. But these are collisional electrons. These are electrons that aren't going to go too very far before they collide and scatter. So you don't think about them as particles, you think about them as part of a fluid, no matter who you are. And then you say, well, how's a fluid staying way up there with such a high temperature? And that's an interesting question. These guys here, they're not part of a fluid because they have so much energy. We saw that they don't meet another particle for 300 megameters, 500 megameters. This actually goes up to 80 kilovolts. That's probably some number of solar radii before they would ever meet another particle at the coronal densities. Okay, if we're talking about lower energies or densities are higher, then we just have to worry about the thermal parts, and then we're doing fluid dynamics. The energy is then being transported by electrons, as I said, but in the much simpler framework of thermal conduction. That is, the flux of heat, the energy flux, is given by the thermal conductivity times the temperature gradient. And I put a matrix here because the heat is conducted almost entirely along the magnetic field. The amount of energy transported across the magnetic field is 14 orders of magnitude, which is basically 0. So you get heat transported only along the magnetic field, but down the temperature gradient, from this 17 million Kelvin stuff down to the 100,000 Kelvin stuff there. Okay? This is thermal conduction, and it is what we're going to talk about driving the evaporation front. The reason I'm going to do it this way is it's just easier to talk about fluid equations. Does everyone agree? Than talking about Vlasov equations. Yeah? Electrons in a plasma. Essentially, the reason there is thermal conduction in anything is you have a random walk of heat. And you have places with a lot of heat and places with a little heat. And the heat is not going from hot to cold, regardless of what you've heard in thermodynamics. The heat is going in every possible direction. It's just that when you have a lot of something and a little of something and things random walk, it tends to spread out and get from the hot to the cold. The things that are doing all the walking in a plasma are electrons. They're moving so much faster, they're carrying all the heat. What I have assumed now is that there's only thermal population. Yeah. That's just saying it makes my life easier to just talk about the thermal population. We could do the whole argument over with a non-thermal. They just basically go streaming straight down and hit the bottom and repopulate it. But I think it's an easier task on my part to explain, and both have the same ultimate effect. But this will be a little bit easier to explain. Okay, so far so good? All right. Before this thermal conduction happens, I want us to really simplify the picture and say we have two parts. We have the corona. I talked about this. The hot corona, I'll just say for ballpark numbers, it's 1,000,000 Kelvin before the flare goes off. And a cold chromosphere, it's 10,000 Kelvin. So the temperature drops as I go from hot to cold. The pressure is roughly the same, so the density goes up. The mass density goes up from a very low value in the corona to 100 times more dense in the chromosphere. That's why it's able to stop those electrons, but here it's just going to be a reservoir of cold stuff. Let's not go into that. Let me just show you a movie. And this has a lot of moving parts to it. Focus on, this is the density. Here is the hot stuff over here. It's up at 2,000,000 Kelvin actually. Drops down to maybe 20,000 in this case. The density goes up like that by an order of magnitude. When the thermal conduction front comes in, it hits that. You see this beautiful evolution in density, and this is the velocity in megameters per second. And you'll see it starts out at 0, but when the heat hits it, it drives stuff upwards and it drives stuff downwards. This is very characteristic and important to understand. And I'm going to build a very simple model of what just happened. We have this nice jump in temperature and jump in density, no jump in pressure. I have thermal conduction, which is actually carrying an increase in temperature down into this interface. Eventually it reaches it and goes through it, and we basically have an interface where the temperature is roughly the same. The density nothing has moved because the thermal conduction happens so quickly. So the density has a jump. That means there's a big pressure jump. A big pressure jump with no motion, no change in density. This is what's known as a Riemann problem. Okay? A Riemann problem is, well, let me just jump to a simplified picture of a Riemann problem. A Riemann problem, we have a nice reservoir here with a happy sailor on top of it. We have a dam. We have someone downstream. That happens to be Riemann. So Riemann's problem is the following. What happens if this dam breaks? He's in trouble, right? So, in fact, the way you solve a Riemann problem is you evaporate the dam instantly. So now you just have a discontinuity, in this case, in the depth of the water. Okay? No velocity. So I evaporated it essentially instantaneously. So the fluid is not moving yet, but it will. In simple words, what's going to happen to Riemann? What's he going to see? He's going to see a wall of water. How high, this is the real key, how high will be this wall of water? Who thinks it will be a 10 meter, 9.5 meter tall wall of water will hit Riemann? Who thinks the answer to the Riemann problem is the wall of water is 10 meters high and it washes over him? Anyone? Okay. Who knows how high it will be? That's tough because you have to solve a Riemann problem. It turns out the solution to a Riemann problem, when you have this initial condition that is discontinuous, the discontinuity decomposes itself into a number of things. When we were talking about co-rotating interaction regions, we had a discontinuity in velocity. It decomposed itself into two shocks, one going each way. In this Riemann problem, the wall of water decomposes itself into two waves. One is a shock. It is a 4 meter, in this case I worked out all the numbers, it is in fact 4 meters high, wall of water that's propagating at 8 meters per second. Okay, that's 15 miles an hour. So, you know, if he was an Olympic rower, he could outrow that. The wave speed of little ripples in this water is 2 meters per second. The shock is moving supersonically. This is a shock, basically. We all know that shocks move supersonically. That's what this is doing. But in addition, there's something known as a rarefaction wave. Okay? That is a linear change in the velocity. So the velocity here is still 0. The sailboat still doesn't see any velocity, but there is a wave propagating towards it. The rarefaction wave is moving the other way. The Riemann problem almost always has waves going both ways. Right? It had a discontinuity at one point. The rest of the fluid must learn of that. There must be information that propagates out and tells the rest of the fluid. The rightward propagating motion is a wall of water 8 meters tall. The water behind it is moving at 7 meters per second. Okay? This is just the way it works. That is the end of this. And so we have a slope that goes from 0 meters per second. And in the rarefaction wave, all of the water is moving to the right, even though the wave itself is moving to the left. That's why it's a rarefaction wave. Eventually, it will reach, it's moving 10 meters per second, it's moving at the linear wave speed. Rarefaction waves do that. They move at the linear wave speed, 10 meters per second. So this sailboat will be hit much sooner than Riemann will be hit. Well, no, not much, a little bit sooner, because that wave speed is faster. Got it? This is a dam. Now we're going to go to the chromosphere, which, let me back up, is basically a discontinuity in pressure, just like Riemann was facing. We have low pressure to the right. This is the hot corona. We're going to get material moving upward towards the hot corona. We're going to get a rarefaction wave moving downward. Which direction will the plasma move in that rarefaction wave? The wave is moving downward. The plasma is moving upward. Everyone follow that? That's how rarefaction waves work. So it will also drive upward flow, but at a lower velocity. And the way we're going to solve it, the only thing that comes into this Riemann problem solution, one of the only things, is what is this jump? And it is basically, in this example, 100 to 1. Okay? In Riemann's problem, it was 20 to 1. Very similar math. Here is the picture of the density and the velocity in the solution to this Riemann problem. It's slightly different. You'll see the velocity increases linearly in the rarefaction wave. Then there's a shock, and there's this shock where The velocity is 0 here, and it is at its asymptotic value over here. This is the evaporation shock, moving upward. This is the rarefaction wave. It is moving downward, but the flow is going upward. Well, except there's one more shock in this problem. This is called the condensation shock. That layer of heat is still moving downward and still trying to get down into the chromosphere, and so there is a shock there as well, and that actually is moving leftward and the fluid is moving leftward. So this rarefaction wave has both downward and upward flows. This is very important in that. Here are the mathematical expressions, and these are just very simple expressions that come out of solving the Riemann problem. The shock, if you went to the Rankine-Hugoniot conditions, I think this will be the third time you've heard it in this series of lectures, the density jump will be a factor of 4. That's just what happens in plasmas. It's a factor of 4 jump in density. It turns out that the velocity with which this moves is square root of 3 times. A is the isothermal sound speed. I don't want to go into all the math here, but I just want to show you something that's very clever. When I put all this together, I don't yet know what the Mach number of the shock is. It turns out the Mach number of the shock has to satisfy this nice little equation. Okay, it is for those who know some detailed math. This is a transcendental equation for the unknown m, the Mach number. Involves only one thing, that ratio, 100 to 1. Transcendental equation, oops, hit the wrong button. Turns out its solution is very insensitive. It has an exponential in it, so the solution is going to have a log in it and a log of a log. I got all excited about having an exponential of an exponential. Now I have a log of a log. So my work is done. I'm going home to Montana. Yeah. So anyway, we can solve it. It just basically is always around 2, right? The Mach numbers we get are always somewhere around 2 to 3. Supersonic flows, has to be. The only thing driving it is pressure. We saw that with the wind problem. When you drive things with pressure into low densities, you get supersonic flows. These are supersonic. Yeah? R is the ratio of the density ratio that we started with. And it's the only number really in this problem, this ratio. Yeah. And so we really know the chromosphere is about 100 to 1. So we do know the Mach numbers are probably going to be about 2.5. I will skip through this because basically this is me translating the Mach number into a flow velocity, but show you that for a real series of runs, and these are going back into the 80s, Peter McNeice, a few in the 90s, my own runs in the crosses, which I did just 2 years ago. The prediction, which I did skip over, I will admit, is that the evaporation velocity and also the shock velocity goes as the amount of energy that's created this to the 1/3 power. Okay? With a coefficient that we don't determine, but I take all these runs and you determine that it's 0.38. It's a dimensionless coefficient. So at least in this simple picture of evaporation, when I have flare fluxes of this magnitude, I get flow speeds in kilometers per second that are hundreds up to 1,000 kilometers per second. That's based on the heat being transported downward and driving evaporation. Okay, and you do see that. Here is a paper by, I'll show you here, it's Milligan and Dennis. Evaporations, these are the foot points, this is the Resi observations. So this isn't exactly a thermal source, but the idea is very similar. Here's the condensation flows. This is the Doppler shift observed at different temperatures by dint of using different ion species. So helium-2, which is hydrogen-like helium, is roughly 80,000 here. I think they put it at 60,000 Kelvin. It is moving downward at 30 kilometers per second. That's the condensation flow we talked about. Some of the cooler, hotter ions, like oxygen-6, magnesium-6, are moving downward, roughly that, maybe even a little faster. And then this is the evaporation flow. This all fits into this picture of the Riemann problem being solved by having heat go down, hit this place where the density is changed by 2 orders of magnitude, and then driven upflows and driven downflows. And it is hundreds of kilometers per second. With my scaling, if we knew this was the asymptotic, the hottest evaporation, we would be able to work out what the energy flux was. Remember, all of this comes from energy flux. So we've now connected that to the most important signature of a solar flare, which is the chromospheric evaporation. It is probably time for a 5-minute break. So let's all just step outside, stretch our legs. Back here in 5 minutes, and we'll pick up with the fourth part. We only have the cooling, and then I want to go over some flare statistics. So we're doing very well. Yeah. People with me so far, I realize there's a lot to digest in solar flares. I've spent a good part of my career studying solar flares, so it's hard to do it in an hour and a half on a Saturday morning. But is this following at least a comprehensible trajectory? The next part, the last part, is a bit easier to understand, and it is certainly the most photogenic thing we see. So we've gone from having the energy which has been stored in the magnetic field released through magnetic reconnection. So we've got magnetic energy converted into other forms. We then had some of that energy transported down along the field lines, either through non-thermal electron precipitation or through heat conduction. It reaches the chromosphere and drives this evaporation, which causes supersonic flows of very high density material. And actually, behind the shock gets high density, and that rarefaction wave had way higher densities still. So if you look at, this is log of density. There's the jump from the rarefaction wave, from the shock, sorry, which is not super high Mach number, so it's not necessarily a jump of 4. And then this rarefaction wave is where most of the density jump occurs. So that loop is eventually going to get hit with a lot of density, very high densities, and then it cools off, and when you see it, we've been talking about tens of millions of Kelvin. This is 1 million degree plasma. So you must be seeing it after it's cooled quite a bit. And let's play that movie once more, because it is, in my opinion, a very cool movie. We are just seeing here, we are seeing the evaporation. The reason it's so bright at 100,000 Kelvin is because the density has risen up so high there. Here, we see these beautiful loops. These are the results of the magnetic reconnection, and then basically those field lines that are left behind by the magnetic reconnection. Just make a little observation here. Here is an early phase, 1123, and the ribbons are actually only present in this portion. They have yet to form way out there. So this is an early phase of the formation. We don't see any loops here because this is almost the exact same time. Sorry, these two instruments on SDO, they have 8 telescopes. They stagger the exposure times because they can't operate them all simultaneously. So we get a slight, couple second difference here. You can actually make out the ribbons at 1 million Kelvin, and why not? That temperature is rising very rapidly from very low temperatures up to tens of millions of Kelvin. It has to go through intermediate value theorem. It has to go through 1 million. So you can actually make out the ribbons in 1 million Kelvin plasma. Let you in on a secret. Before we had SDO and we could observe all these temperatures at once, we had TRACE, which was an awesome experiment for 150 million Kelvin, $150 million. But we could only operate it at 1 wavelength at a time. The movie I showed you of the Earth Day flare, it was just operating at 193. But you can see ribbons, so we can play these tricks even with older data. We much prefer to play them with these new data here. Okay, that was a little aside. You can see this is basically the feet of the loops that are being formed. Now, you see at 12:08, 44 minutes later, you see just those loops, right, connected to there. So it takes 44 minutes for it to get from wherever it was forming these evaporation down to 1,000,000 Kelvin. This is the last part of the story. Here's a very simple simulation of a single loop being heated, having evaporation, and then cooling off. What I plot here is the density, electron number density in units of 10 to the 9. So that's actually 10 to the 10, sort of that number I was talking about, the amount of plasma you really expect in a solar flare loop. Here's the temperature. It starts off at a couple of megakelvin, goes up not quite to 30, nice temperature. This is where the heat is being injected. Okay, this is, and I'll get into this, this is where that heat is driving evaporation. In this model, it is driving it entirely through thermal conduction. It is transferring heat from the top to the bottom, and so the top is getting colder and the bottom's getting hotter. So you see the temperature drop there. Then I basically blow up the scale. That all happened in about 13 seconds. I blow up the scale so we can go out to, 13 minutes. We can go out to 2 hours, and then the loop just gets cooler and cooler and cooler. The governing equation for all of this, the time rate of change of the energy density. Energy density is density times temperature times a specific heat. Okay, that's basic thermodynamics. This changes due to changes in the energy of the loop, which take three forms. There's enthalpy flux. This is flow into or out of the region I'm looking at, carrying energy heat with it. That has the specific heat, but the specific heat at constant pressure. That's why it's called an enthalpy flux, not an energy flux. Density times temperature. Radiation. We talked about this on Tuesday. The plasma is losing energy through radiation. There's that great, crazy radiative loss function, lambda. Looks really nasty. There's debates about exactly what it looks like, but we have pretty good agreement on that. Density squared, because it has to do with collisions of things. If things are going to collide, there have to be two of them. I always point out the number of collisions per square mile in a city goes up as the number of cars squared, because every collision involves two cars. I'm not talking about car-pedestrian collisions. Those are, yeah. Anyway, so density squared. And then there's that thermal conduction, which has played such a big role. Gradient of kappa times grad T. So all three of these things are contributing to the energy. One of the things we can do is just take a ratio of this energy divided by the loss rate, and if I just use the conductive cooling loss rate, I get what's known as the conductive cooling time. And that scales as the density, as the length of the loop squared, and as the temperature to the minus 5/2 power. So if I increase the temperature of the loop by a factor of 4, I make it cool 32 times faster. So the conductive cooling time is very temperature sensitive. If I use radiation in its place, I get something that scales actually in the opposite direction. As I get hotter, the radiative cooling time gets bigger. This was the crisis we had that even led us to believe there must be a corona. As things get hotter, they cool less well. They don't radiate as effectively, not cool, radiate. So our problem was basically if we only included this, we couldn't even explain how hot stuff could be in the corona. It's all unstable. This is the thermal conduction. If I plot those two timescales, I draw an arrow and say, well, if it's cooling only by thermal conduction, it should go down along this magenta line. Only by radiation, it should go along the blue line. You see, it's going along the magenta line. It's the shortest of the two cooling times. That's what's dominating it. So during this evaporation phase, and we just finished talking about the evaporation phase, it is thermal conduction that's doing all of the cooling. It's also driving the evaporation. Later on, the two have almost the same rate. This is very puzzling. But in a way it makes sense. If I take the radiative cooling time divided by the conductive cooling time, I get something that goes as the 4th power of temperature. So when the temperature is high, the radiative cooling time is huge compared to the conductive cooling time. I'm in this zone where only conduction is cooling my loop. Eventually, this ends up becoming 1. Right? So we have what's known as the conductive cooling phase, and then we switch over to another phase. You might notice also that is the point at which the density peaks. So the temperature in a flare peaks first, the density later. Now you see exactly why that is. Because during the conductive cooling phase, that conductivity doesn't actually remove heat. All it does is transport it, and it transports it down to the chromosphere, evaporates material up. The density keeps going up until you cross over into that other phase. Now the density is going to start falling down. And this is a plot where I plotted density. I love doing these plots, as you could probably tell. This is density plotted as a function of temperature. And the loop goes up like this and does like a little, it goes like this. Does a little loop, goes, right? This is, temperature goes up at constant density because when I'm heating so fast, there's no time for this evaporation to change the density. So I heat along that curve. Then this is the chromospheric evaporation we just studied, and then I fall down, both temperature and density fall down together. I want to talk about how that works. Yeah, loop's cool. If I reach a phase where I'm not going to evaporate anymore, then it turns out the flow velocity goes down. I have a very slowly moving plasma. So in the energy balance of these 3, I can throw out one of them. Right? The enthalpy flux is no longer playing an important role. So now we're back in territory that should be somewhat familiar. We have radiation and we have conduction. This was our static loop problem. The other thing is if there's nothing to move flow around, that must mean the pressure gradients are all fairly small. The pressure is fairly uniform at this point. Pressure is density times temperature, so the energy density is fairly uniform. That's why it doesn't need any flows. Everyone's sort of on the same page when it comes to how much energy they have. This term over here then, not that it's negligible, but it's not a function of position. It's a simple function of time, which I could think of as just a heating term. Well, actually, it's cooling, so it's minus a heating term. Now we have exactly the same equation we had on Tuesday. Right? This is an equilibrium loop equation. Heating, which is actually uniform in space, radiative losses, conductive cooling. And we solved that problem, where I showed you the solution. In the solution, the density of the loop went as temperature squared. That's just the solution to that differential equation. So we must be back in a situation where density goes as temperature squared. That's why density and temperature fall off together. Actually, if you follow that curve, it works very well. The other thing you'll notice is if I plug in density going as temperature squared, the ratio of radiative to conductive cooling times has now reached an asymptotic value. And that asymptotic value is very close to 1. I didn't go into the I wouldn't say it's a subtle argument. It's not complicated, but it's subtle as to why those two should balance in equilibrium, but they also balance in the flare. So that's why we end up at this cooling phase. We now have a cooling along this curve, density, temperature squared. So the loop gets cooler at the same time its density decreases. The density is dropping due to flows, so this term is not 0, but the flows are slow enough that it's taking 2 hours to cool this particular loop out. And this is very, now with SDO observing at 8 different temperatures at once, we have a beautiful way of verifying this. This is the Boxing Day flare. My collaborator, Zhang Chu, prepares these plots all the time. This is the curve in black is, sorry, it's not black, but it's red, is the plasma at 10 million Kelvin. The gold is 6 million Kelvin. The green is 3 million Kelvin. This blue is 2 million. The purple is 1 million. This is how bright this image looks at each of those wavelengths if I integrate all the pixels. And you can see it is cooling from 10 to 6 to 3 to 2 to 1. It's cooling. And you see the delays here. In the observations, it hits, well, this is when the ribbons are bright. That's when the heating is actually happening at 1132. It reaches 3 million Kelvin at 1220. So 50 minutes later. It takes 50 minutes to get from there to there, and then another 24 minutes to get to there. This is it cooling, and very slowly, because that radiative cooling time is so small. So long, sorry. All right. So how's everyone? That is the flare, a single flare in model form. Okay. If we're happy with that, I have 13 minutes left. So I wanted to look at the population of lots and lots of flares. So I'm going to ignore the details of a single flare and look at this curve here, which is a month worth of flares. And rather than look at the details of each flare, I said the flare is really a flare because the X-ray flux goes up. I should also explain this is sort of a baseline. This is sort of how much X-ray flux is happening when there is no flaring. This is an order of magnitude above it. This is 2 orders of magnitude above it. So the truly impressive thing about a solar flare, as I said, it enhances the X-ray luminosity. It's a fairly small portion of the sun, and yet the overall output of the sun goes up 100-fold. Overall output, well, at these very high energies, it goes up 100. The whole star is 100 times brighter. That's why we see stellar flares, because we see other stars, and they actually can have much bigger flares. Okay, but let's just look at how often that happens. And the way you do it is I'm going to form some amplitude bins. Wow, these colors really get washed out. So there's one bin up here that is X flares and above. There's another bin here that is sort of 3 times 10 to the 5 to 10 to the minus 5, 10 to the minus 4, a second bin. And a third bin here, which you actually can see. And I'm simply going to count the number of times the flux goes into each bin. So for the top bin, I can count to 1. Right? There's 1 time over the month of April that we got a flare in the X category. How many for the next bin down? 4? Everyone count to 4? 1, 2, 3, 4. Didn't quite make none of these. Yeah, so I get 4. I won't make you count the next bin down, 11. Okay, so we have this progression, and this is very common in all across the sciences. We have very infrequent big things, more frequent medium things, and extremely frequent small things. I can actually reduce the bin, take a longer baseline, and here is the plot of all flares between 1976, the bicentennial, and 2003. And you can see the bins are fairly small here. This is X flare. This is 10 times the X flare. We get a power law. A power law in the frequency of flares. Now, it breaks over here, but remember, at the time we were talking about, the baseline was up around here. At various times through this, what is this, 30-year time span here, that has happened more than once. So these are undercounted. We're sure that this range of energies, which has been reported here quite well by Mike Wheatland, but we really trust this portion where we think we're getting all the flares there are in that 30-year period, 10 to the minus, or S to the minus 2.5. I can integrate this from infinity back, and that's known as the cumulative distribution function. Of course, I integrate a power law, I just get a power that's 1 higher. So S to the minus 1.15. So that tells us right away that an X flare is 14 times less likely than an M flare. There you go. Okay, this is just the power law distribution of flares. And if you follow that, that's 10 to the 1.15 is 14. I had to work that out on a calculator, etc. Why is this? We don't know yet, but there's a really amazing, interesting parallel. This is known as the Richter, shoot. I can't remember there's a Russian name associated with it too, and I'm blanking on it, law. This is the magnitude in the Richter scale. You've all heard of earthquakes, they come in the Richter scale. It's actually a logarithmic scale. So a magnitude 6 earthquake is a factor, I think it's like 30 times more energetic than a magnitude 5 earthquake. Magnitude 7, an order of magnitude higher still, or that much factor larger than magnitude 6. The frequency of earthquakes of different magnitudes follows a power law. Instead of 1.15, this is a power of 0.68. Now remember, this is earthquake magnitude, which is logarithmic, I should say. So it's a power law if you unlog this, if you exponentiate it. Yeah, there's no reason these two numbers should be the same because they're measuring very different things. But earthquakes have this known power law distribution. And so I don't think it's fair to ask a solar physicist to explain the power law distribution in flares when human beings have known about earthquakes much longer, and yet nobody has convincingly explained this. Okay? So they go first, we'll come after that. But there are a lot of interesting scientific explanations for this as well as this. A lot of interplay between them. But this is just a known property of earthquakes, and it's also a known property of solar flares. Given the known property of solar flares and what I said, X flares are 14 times less likely than M flares, C flares are 14 times more likely than M flares, blah, blah, blah. This gives you a forecasting tool. And it's along the same lines as the forecasting tool for earthquakes. Now, you'll all say, Dana, they can't predict earthquakes. And I would say, in a way they can. I will do one for you right here. If you live in Tokyo, you can expect some earthquakes. Right? If you live in Branson, Missouri, maybe not so many. Right? I'm just using the power law in my head that the small earthquakes are more frequent than the big earthquakes. So if you have lots and lots of small earthquakes, you should expect a big earthquake once in a while. If you're in Branson, Missouri, the last earthquake there was in the 1800s. And it was kind of big, but okay. Frequency, very low. Future frequency, very low. And we can do the same with flares. And here is Mike Wheatland's tool for doing exactly that. What he's done is actually taken that same data set, and he has used his tool and basically made forecasts using only past data. And he comes up with the number of days on which he would have said there is a 50% chance of an M flare on this day. And then he looks at the real data and says, how often did he get that right? So here's the number of, the diamonds are the number of days on which he predicted an M flare was likely. And the solid line is the number of days on which X flares genuinely did occur. You can see he does a reasonable job. Yeah, so you can put this to real practical use. You can figure out how likely it is you're going to see an M flare. And what his tool does is just basically say, look at all the smaller flares and just look at the frequency of those and extrapolate upward, and I'll tell you how likely an M flare is. And since the rate of all those flares, the rate changes over time, the prediction changes over time. Same deal with the X flares. Okay, so we are done then. This told you about solar flares. It also got to the statistics. So to recap, a flare was a sudden brightening, rise in the level of X-rays coming out of the sun. Okay? It followed a pattern where the energy was released, The coronal magnetic field released its magnetic energy through magnetic reconnection. It was transported downward, and then we got the chromospheric evaporation and the loops. That is the flare as we know it. And then the loops cool, and we actually see these beautiful loop images much later on. And the occurrence so far is something like an earthquake. I couldn't tell you, yes, in Tokyo you will experience earthquakes. I can't tell you that on Thursday, December 5th, 2020, there will be an earthquake at 3 in the afternoon. We don't have that technology. But I will say, live in Tokyo, live with earthquakes. Okay? Same is true with flares. You're like, on the days where you see lots and lots of flares of small amplitude, better get ready for a big flare. That's very likely on those days. Days when there's not much going on in the sun and you don't see many small flares, probably not going to be a big flare. Okay, let's take a half-hour break and get ready for our lab. Any questions? Any questions on flares? All right, it was that clear. You now do know, as promised, everything